All right, continuing on our whole chapter of trends, the next trend we want to talk about is ionization energy. So the name kind of gives you a hint. It's going to be making an ion, ionization, we're making an ion, and it takes energy to make an ion, okay? Because remember, you're either gaining or losing an electron. Ionization energy specifically, though, is removing. So it's the amount of energy to go into an atom and remove one of those outer electrons. So ionization energy is the amount of energy required to remove an electron from an isolated gaseous atom. So if I'm doing the first ionization energy, so if I wanted to, I have an element, say this is my element, I'm just saying E for element. It's gonna take energy to do this. So I have to put in some energy. Remember, we have that equation from last chapter that talked about energy, and energy was equal to HV. So when we talk about energy, we represent it as HV. So I have my element, I put in some energy, and when I put in the energy, I'm gonna pull out an electron. So I have my element, I put in some energy, and I'll pull out an electron. When I pull out an electron, I get the electron, and then what's left over is a cation. This amount of energy that it took to do this was my ionization energy. Okay? That was the amount of energy it took to remove the electron from the first time, that first electron. I could also remove a second electron. The second electron, though, that I'm removing isn't going to be from the neutral, because this is the first one. Now I take my element after I remove the first one. This is what I have left over. I'm going to remove another electron. So I've got my cation. I'm going to put in some energy. I'm going to remove another electron. When I remove another electron, now he has 2 electrons missing. So he is going to be a +2 cation. Okay? So this would be the second ionization energy. Now let's talk about how these energies relate. The first ionization energy is going to take energy, but it takes a lot less energy than the second, okay? Each successive ionization energy requires more energy, okay? So this energy is going to be a lot less than this one. The reason is because here, I'm just removing an electron from a neutral atom, okay? Neutral atom. But here I'm removing it from a cation. And so, think about this. You've got your outside electrons. The first one I take off is going to be the furthest from the outside, from my nucleus. The next one is going to be closer, so he's more attracted to my protons. So if he's more attracted, it's going to be harder for him to be pulled off, because he's going to have a higher Z effective. So the first one's easier to pull off, the second one, and the more you pull off, the closer you get to this to the nucleus, the harder it's going to be, to the point where you're not going to pull off any of them. Okay? So what you need to know is that first one is not as hard as the second one. So let's talk about trends. This is just talking about if I'm removing multiple electrons from the same. But what if I wanted to say, what is this element or is this element have a higher ionization energy? Which element takes more energy to pull off an electron? All right, so let's talk about a trend. I'm going to tell you the trend, but what I want you to know is that as I go down this slide, this doesn't work as much. This works most of the time. This is the one you want to follow. So these are kind of like rules. So when you're thinking about which rule to follow, this rule is the first rule, then this rule, then this rule. So this is like your Trump rule. So I'm going to show you the rules in the opposite order of importance. So then when we do a problem, this is the first rule, then this one, okay? So there's a trend. So if you wanted to know the ionization energy trend, the trend is that as I go from left to right, it increases. That's due to that effective nuclear charge increasing. As those electrons fill the protons more, it's hard to remove them. And then as I go down a group, my ionization energy decreases. This is due to the size. Remember, when I go down a group, my size gets bigger. So that means these electrons are further away from the nucleus. So they're further away, they don't fill the protons as much, so it's easier for me to remove them. So that's my trend, okay? But remember, that's my last resort. I only use the trend as a last resort. So like I want to use this guy first, then this guy, then this is my third option. Second option is, what if I'm trying to remove from the same energy level, like N level, but at different orbitals? It is harder to remove from an S orbital than a P orbital of the same N quantum number. So I'm saying it's harder to remove from like an S than a P if I'm saying like 2S and 2P. So it has to have the same N quantum number. So 2S is harder to remove from the 2P. This is the most important rule. Most important rule is what my shell is like. Am I filled, half filled, or partially filled? So this is where those orbital diagrams matter. The most stable, what I want to be is I want to have all of my orbitals filled and everybody paired up. So everybody's got 2 electrons and they're paired up. That's my most stable. So if I am completely filled up, all my electrons are filled up, and you're trying to go in and take one away from me, I'm not going to be happy, because that's what I want. I want to be completely full. So if it's filled, it's going to be really hard for you to remove an electron. It's going to be really hard because I'm happy. I'm happy being filled and you're messing with me. You're screwing me up. If I'm half filled, I'm not as happy if I'm filled, but I'm way happier than if I'm not balanced. Okay? So if I'm half filled, think about a p orbital. It has those 3 lines. If each one of those had 1 electron, 1, 1, and 1. So each one of them had 1, then all of my orbitals would be half full. Okay? So if I was half full, I'm not as happy, but I don't want you to mess with me. I'm like, look, I'm not perfect, but I like where I'm at, and I don't want you to screw with me. So it's going to be hard for you to remove that electron also. If I'm partially filled, meaning I don't have all of my orbitals full or all of them half full, I don't really care. It's still going to take energy for you to remove, but it's the lowest. So it's easier to remove if I'm partially filled. All right, let's look at an example. So on the next lecture video, we're going to work out this example just to keep our videos a little shorter.